Hey everybody, we're live in stereo. So now we're going to look into the reactions for alkenes. We're done with how alkenes are formed, and I'm going to give you guys the mind map once over again, all over again. Up until now, the mechanisms that I've taught you are not part of your course for alkenes, right? I've taught you guys two elimination reaction mechanisms, both of which are not part of your say it, your course, right? Thank you. So we're going to quickly look into our mind map, and then we are going to look into reactions that alkenes undergo. So mind map again, crude oil. You have what? Crude oil. What is the process that you make sure that happens to get alkanes? Crude oil is mostly a mixture of alkanes, and then you fractionally distill crude oil and you end up with alkanes. Then from alkanes we did reactions of alkanes. Combustion I normally don't write in my mind map because we already know that alkenes both will undergo combustion. But when alkanes form, you can literally form what? You can literally form alkenes from alkanes. How do you know that, sir? I know that because there's a process called cracking, or you can also call it pyrolysis. What were the conditions? Absence of oxygen. Why absence of oxygen? Because if oxygen is present, you're going to undergo combustion, since alkanes are fuels. Then you need high temperature and high pressure, and you also need what? You also need a catalyst, which is aluminum oxide, Al2O3, or you can use another catalyst nowadays which is very famous in industries called zeolite. Because zeolite, if you're using zeolite, you actually need to provide it with lower pressures. It saves energy costs. It saves you guys a lot of money, right? And then we studied another reaction for alkanes. We studied number 1, combustion. I'm not writing combustion in my mind map. Number 2, cracking. And number 3, free radical substitution. And through free radical substitution, you ended up with haloalkanes. And what were the conditions for it? You needed UV light to provide it with the activation energy, and you call this reaction what? You call this reaction as FRS, free radical substitution reaction. And then we learned how alkenes are formed. So one way of forming alkenes was by the cracking of alkanes, and the other way, two other ways were from haloalkanes, you could literally form alkenes, and from alcohols, you could form alkenes. And both are effectively what? Both are effectively elimination reactions. So both effectively are elimination reactions. And for alcohols, you can also call it dehydration. You can also call this fella dehydration reaction, because effectively what happens is a H2O is removed, right? You dehydrate it, you take it, you rob it off of H2O, you strip it off of H2O, right? And so how do haloalkenes go into alkenes? We know the conditions for it. You use sodium hydroxide, ethanolic, and you heat under reflux. We know why we heat under reflux: to prevent the volatile reactants from escaping. You have ethanol, you have haloalkanes, they're both volatile, we don't want them to escape, so we use heat under reflux. And here we either use aluminum oxide as a catalyst, or we use concentrated acid, normally concentrated sulfuric acid or concentrated phosphoric acid, and we heat under reflux. Normally I prefer heating under reflux because, again, alcohols are highly volatile. We don't want alcohols to escape. Now these two reaction mechanisms weren't part of your course content, but if you want me to quickly recap it, I can absolutely do that. And the reason why I've taught you guys the reaction mechanism for these two even is to just give you an idea of why you're using sodium hydroxide ethanolic and why you're using concentrated acid and heating under reflux, or this and heating under reflux. And the only reason why I taught those mechanisms was to get this across your brain, because what really happens is, the reason why you use sodium hydroxide or potassium hydroxide is because that if you take any haloalkane, which looks something like this, we said that the only way an elimination reaction would take place is if you have a hydrogen directly bonded to the adjacent carbon, right? And only then would the H and Cl be removed. But you don't end up with H and Cl, do you? You end up with an alkene, and you end up with sodium chloride plus H2O. And this is the reason why I taught you guys the mechanism for it, because this is the reaction for this is the complete reaction. You don't just need to know that an alkene forms, you also need to know the byproducts. The byproducts is not HCl, and the reason for that is pretty simple. The reason is pretty basic, is that the OH in sodium hydroxide, this OH right here, this can act as a nucleophile because it has a lone pair of electrons right here. This OH can act as a nucleophile because it has a lone pair, and it can also act as a base because you know hydroxide ion is a base, right? So here, because we want it to act as a base, we use ethanolic conditions. This is very important to know these things, right? So we dissolve sodium hydroxide in ethanol because we want the OH minus to act as a base, not as a nucleophile. And in order for it to act as a base, it has to accept a hydrogen ion. So what it does is it attacks these two electrons right here. It attacks this hydrogen right here. Now hydrogen can't make two bonds. So what it does is this hydrogen starts to break the CH bond, right? So how does it break the CH bond? This bond right here, this breaks, and this bond converts into a double bond right here because that's more favorable energetically. So what happens is the OH minus accepts the hydrogen ion, forms H2O, and these two electrons go here, form the double bond. Now the problem is the right carbon has now made 5 bonds, 2 here, 3, 4, 5. Now you either break the CH bond or break the CCl bond. We know the CCl bond is weaker than the CH bond, and that's why 2 electrons go here. And when they go here, you end up with a chloride ion which bonds with the sodium ion and ends up with NaCl, right? So this is actually the mechanism for it, which you don't need to know. Similarly, I've taught you guys the mechanism for the alcohols. You don't need to know this mechanism as well. The only reason why I've taught you guys the mechanism is to get you guys, is to make you guys understand that, why H2O forms as a byproduct, because when dehydration takes place, you end up with an alkene and H2O. When haloalkenes go into alkenes, you end up with H2O and you end up with a salt, sodium chloride, right? In this particular case, done. Now, today what we are going to do is we are going to study the reactions of alkenes. Now alkenes undergo certain reactions, and this is largely O levels and IGCSE. You've already studied these reactions in O levels and IGCSE, which number one is combustion. You all know what combustion is. We've studied it in alkanes chapter. I'm not gonna go on into the definitions for combustion. You just need to know that since alkenes are fuels, they can undergo combustion, right? Normally, this is a fun fact for you guys, normally we don't use alkenes as fuels. Normally don't use alkenes as fuels, because once I remember it was tested between alkanes and alkenes, you normally use alkanes as fuel. Petrol is basically octane. You use alkanes as fuels, you don't use alkenes as fuels. Do you know the reason for it? These things weren't taught to you in O levels. Now we have to teach it to you because they are tested in MCQs. So normally, why don't you use alkenes as fuels? Do you guys want to use your brain for it? Understand that when alkenes are burnt, they burn with a smoky and sooty flame. They burn with a smoky or sooty flame. Now, why does this happen? Let me tell you. Just give me a moment. So, as I was saying before, I got rudely interrupted by a call. These alkenes, they burn with smoky or sooty flames. Do you know why? Use your brains. Do you know why? Because each alkene has a smaller percentage of hydrogen compared to its corresponding alkane. For example, I'll tell you, you have an alkene which is C2H4, which is ethene, and then you have C2H6, which is ethane. Between these two, which one has a higher percentage of hydrogen? We know that this fella, alkane, has a higher percentage of hydrogen, right? A higher percentage of hydrogen. And if I say which two fellas between an alkene and an alkane, which two fellas has a higher percentage of carbon? Well, you might say, sir, both have 2 carbon, but no. Both have 2 carbon, but I want the percentage of carbon. You can actually calculate this, right? Carbons is what? 12 times 2, that's 24, divided by the total mass of this molecule, which is 24 plus 4 in this case. 24 plus 4 is 28. Can you give me the percentage here? And here it's 12 times 2 divided by what? 28 plus 2, 30. Right? So what do you get? What percentages do you get here? Multiply by 100%, obviously. What percentage do we get here? What percentage do we get here? Please, can somebody tell me that? Or do you want me to calculate it on my own? Mere khayal se I have to calculate it on my own because some nerdy dumbo jumbos are sitting in the class, not going to help me. 24 divided by 28, you get about 85% carbon, about 85.7% carbon, right? 85.7% carbon right here in an alkene, and you get 24 divided by 30, you get about 80% carbon here in an alkene. So what you realize is alkenes have a higher percentage of carbon compared to alkanes, whereas alkenes have a higher percentage of hydrogen compared to alkenes. So the reason why you get sooty or smoky flame is because of the higher percentage of carbon. You have a higher percentage by mass of carbon in an alkene And you can also say it has a smaller percentage of hydrogen in alkene compared to an alkane. That's why, because of this carbon effectively, that's why it burns with smoky or sooty flames. Because you know that this sooty, this black color is because of these solid carbons. So it has more carbon content, therefore you will see more sooty flames. Right, more sooty flames. That's why you normally don't use alkenes as fuels. Done. This concept is crystal clear. And also one more thing, sir, when you react alkenes with oxygen, C2H4 plus O2, you react it with oxygen, or C3H6 plus O2. You know these reactions, right? You can, or C3H6 plus O2, or C3H6 plus O2. What happens is, you know that if it's complete combustion, carbon dioxide and water is going to form. And if it's complete combustion, carbon dioxide and water is going to form. If it's incomplete combustion, carbon monoxide and water can form. And if it is another type of incomplete combustion, you know, you can also form carbon, soot, solid carbon, and H2O. So this can also form. And balancing, I hope it's a piece of cake for you guys now. The number of carbons that you have must be the number of carbon dioxide which form. The number of hydrogens that you have, hydrogens, half of that would be in H2O. So what should I multiply 2 with to get 6? X is equal to 6 over 2. That's 3. So that's how many H2Os will form, because 3 times 2 is 6. You just need to make sure that the atoms are balanced. And 3 times 2 is 6. 6 plus 3 is 9. So what should I multiply 2 with to get 9? And you can also use the general equation here, 9 over 2. It's bilkul the same as alkenes, right? But understand one more thing, guys, that for an alkene, you need more oxygen. You also need more oxygen per mole of alkene burning. Why do you need more oxygen per mole of alkene burning? Because it's pretty obvious, you know, alkene has a double bond, carbon-carbon double bond. So you need to break the sigma bond, and you need to also break the pi bond. Sigma bond and pi bond both must be broken in order for combustion to take place. In order for carbon dioxide and water to form, you must break the sigma bond as well as the pi bond. And that is the reason why you need more oxygen. Right? So that's the reason why you normally don't use alkenes as fuels. It's because it burns with a smoky or sooty flame, and the reason for that is it has a higher percentage of carbon by mass compared to its respective alkenes, and you also need more oxygen per mole to break the sigma and pi bond. So these are one of the two reasons. Okay, alkenes, they are not normally used as fuels, but combustion can take place, and it's exactly the same as for your alkenes, right? The idea is bilkul the same. The second reaction that alkenes undergo is called addition reaction, right? The ones that we've studied in O levels and IGCSE. And why does this addition reaction take place? The reason why addition reaction take place is because of the carbon-carbon double bond. And what is so special about this carbon-carbon double bond that the addition reaction takes place? I'm not going to talk about this right now, but we know that this carbon-carbon double bond can break and you can add on more atoms to it, and that's why it's called addition reaction. But I'm going to add one more name to it. I'm not just going to call it addition reaction, I'm going to call it electrophilic addition reaction. Now, why am I calling it electrophilic addition reaction? I'll tell you in a while. For now, just think, KR, it's addition reaction, the same addition reaction that you guys used to study in O level and IGCSE. Number one was hydrogenation. The addition of hydrogen is called hydrogenation, right? Then number two was halogenation. This is just O-level IGCSE recap. I'm not teaching anything new. Number three was hydrohalogenation, the addition of HCl or HBr, you know. So hydrohalogenation. Number D was what? Number D is hydration, the addition of steam effectively. Right? These were the four reactions that you used to study in O-level and IGCSE. And by the way, you also used to study, this is number two, I'm going to add number three. You also used to study oxidation reaction of alkenes, didn't you? No, you didn't, you dumbo jumbo. This is something new. So oxidation reaction of alkenes is something new. This you will study right now. You either use cold potassium manganate, cold KMnO4 acidified, or you use hot KMnO4 acidified. I'm just writing what we are going to study in this particular reactions, right? And the last reaction for alkenes was polymerization. And which polymerization? Polymerization. Addition polymerization, right? I'm just writing all of this which we have to study in this particular class, Right? Maybe we aren't able to cover all of this, but we are going to slowly and gradually cover, right? This part is part of O levels and IGCSE. I'm going to quickly recap the O level and IGCSE bit, and then we're going to look into the A level bit of it, right? So this part is O level IGCSE. This part is just A levels. You have not studied this before. And this part, some of polymerization you studied in O level IGCSE, and some advanced concepts you are going to study in A levels, right? But first, let's quickly recap the addition reaction of alkenes from O level and IGCSE, right? Let's discuss the idea of addition reaction. Let's discuss it. Let's first of all look into hydrogenation. Hydrogenation means the addition of hydrogen. Now, why is it called the addition of hydrogen? The idea is pretty simple. The reason why a reaction is called an addition reaction is because a single product forms. That's why a reaction is known as an addition reaction. That's the identification of an addition reaction wherein a single product forms. And why does a single product forms? The idea is pretty simple. If you take carbon-carbon double bonded to each other, let's suppose I took an alkene, which is ethene right here, and I add hydrogen to it, how will this hydrogen be added to it? Sir, what really happens is that this double bond breaks, and you add one hydrogen atom here, and one hydrogen atom is bonded here, and you end up with what? You end up with a beautiful alkene. Obviously, this is not how it happens. Understand, this is not how it happens. This is how you were taught in O level and IGCSE. You're going to learn how it happens this time. But from O level and IGCSE, you must remember that whenever you take an alkene, let's suppose I took C2H4, which was ethene, and I added hydrogen to it, what happened? An addition reaction took place because a single product formed. And why was a single product forming? The double bond broke. Both the hydrogen atoms got bonded to this C2H4, and you ended up with C2H6, two more hydrogens, right? And this is called an addition reaction, and we call this hydrogenation, the addition of hydrogen. Now we know that hydrogen is my reagent, but we also remember from O level IGCSE that we used to use nickel solid as a catalyst, and we used to heat it. Remember, this was the condition for it. We used to use nickel solid and heat it. And one more thing that you need to understand right here. You took an alkene, and when you added hydrogen to it, you effectively made the respective alkane for it. So if you have a 2-carbon alkene, which is maybe ethene, you can make ethane from it by just adding a hydrogen to it, using nickel solid as catalyst and heating it. That's all. That's all. We remember this from O level IGCSE. So from O level IGCSE, if you take C2H4 and you add hydrogen to it, what really happens is you provide nickel solid as you have nickel solid as catalyst, and you heat it. What happens is C2H6 formed. The double bond breaks. Both the hydrogen get added to the alkene, and you end up with an alkene. So from an alkene, you can literally form an alkane. So from an alkene, you can form an alkane, and this is the reaction for it, which you used to study in O level IGCSE. Remember, this is not how it happens. Again, this is just a recap of O level IGCSE. How it happens, you'll study in this particular class. For now, just bear with me. I need to just quickly go over certain ideas. The other thing, this was called hydrogenation, addition of hydrogen, right? The other idea is called halogenation, in which you take an alkene, you add chlorine to it, a halogen to it. That's why you call it halogenation, because a halogen is being added to it. And what happens? What conditions do you need to provide it? Sir, you don't need to provide any conditions. If the examiner were to ask you about the conditions, this literally happens at room temperature and pressure, and even in a dark room. So even if you have not provided any conditions for it, it's dark room, it's at room temperature and pressure, this reaction is going to take place. The question is why? Because understand that this reaction is favorable. This is very favorable. It'll happen at room temperature and even in a dark room. That's why we write these conditions if asked in the exams. Normally you are not asked about the conditions for this particular reaction, but I remember back in 2020, 2019, you used to be asked, what are the conditions of halogenation? There are no conditions. That's why we say at RTP and in a dark room, this reaction will also take place. And why is it known as an addition reaction? Because again, the double bond will break, both the chlorines will get added to this carbon. So C2H4 as it is, and you have two more chlorines being added. And see, a single product is forming. And that's why it's called as an addition reaction. And this is how you went from an alkene into a haloalkane, because this is a haloalkane, right? You have halogen atoms, and you also have the respective halogen atoms bonded to carbon, hence called haloalkane, right? hence called haloalkane. Done? Here, moving on. I just got distracted for a bit, but here, moving on. This is what we studied in O level and IGCSE. And again, we used to remember it like this. If you remember, in order to understand A level knowledge, you first have to remember O level knowledge for it, right? So this is how we used to remember. We used to say, hey, the double bond breaks. This double bond right here, this is going to break effectively right now. I'm going to break it. And one chlorine atom goes here, and the other chlorine atom gets bonded here, right? The other Cl atom bonds here, and this bond breaks. This bond also breaks. The double bond breaks. A Cl atom goes here, a Cl atom goes here. This is not how it happens. We used to just teach it like this because the mechanism was not part of your course, but this is not how it happens. You'll learn the mechanism, don't worry about it. But I just want you guys to appreciate the fact that alkenes could go into haloalkanes if you added a halogen to it. Alkenes could go into alkanes if you added hydrogen to it. That's all. Number C. Alkenes C2H4 could also go into haloalkanes by reaction with HCl. By reaction with HCl, HBr, which is effectively a hydrohalogen. So hydrohalogenation, the addition of a hydrohalogen. Hydrohalogenation means you have a halogen atom bonded to a hydrogen and you're adding that. What would happen? The double bond would break. And what were the conditions for it? This also had no conditions. Hence, we used to write it at RTP in a dark room. Because very, very reactive, very favorable reaction. And so the double bond would break. You're going to add a hydrogen. So from 4, you're going to end up with 5 hydrogens now and a chlorine atom. And this is again a haloalkane. And appreciate the fact that if you add halogens to an alkene, you end up with 2 halogens being added, right? And here, if you add a hydrohalogen, you end up with a hydrogen increase in one hydrogen and one halogen, right? So this is what used to happen. Number 4 was what? Number 4 was steam. Remember the reaction with steam. What was the reaction with steam? C2H4. You added HCl to it. And what were the reactions? What were the, sorry, not HCl, steam, sorry. H2O. H2O gas. The hence called steam. And we used to call this reaction as hydration. The addition of hydrogen. The addition of water, steam. Not hydrogen or water, it's steam. The addition of steam, because H2O gas has enough energy to undergo this reaction, not H2O liquid. So we call this hydration, but it's effectively the addition of steam. And what would happen? You used to use acid, concentrated acid as my catalyst, and we used to have about 300 degrees Celsius of temperature and about 60 atmospheres as my pressure, right? And even in A levels, you know this. And so what used to happen is a hydrogen would be bonded and an OH would be bonded, right? Because H2 is effectively H bonded to OH. So there would be an increase in hydrogen, which is C2H4, and a hydrogen would come, which is H5 now, and OH. And what is this fella? This fella is my alcohol. So realize something. If you look at all of these reactions, and this is an alkene, this is an alkene, 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 alkene. If you look at these reactions holistically, you would see something. If you look at all of these 4 reactions holistically, this is O-level IGCSE. I have not done anything here. You used to use concentrated acid. Remember, on O-level, you used to either use conc sulfuric acid acidified, H2SO4 acidified, /H plus, or H3PO4 acidified. You must have either studied sulfuric acid acidified or phosphoric acid acidified in O-level IGCSE. But I want you guys to look at this holistically. Holistically, when you look at this, you realize that, hey, alkenes can go back into alkenes. How? If you add hydrogen to it, because the only difference between an alkene and an alkane is of 2 hydrogens. Alkane just has 2 more hydrogens compared to an alkene. So how do you go from an alkene to an alkane? Just add 2 hydrogens to it, which is the addition of hydrogen. Hydrogenation. And what happens is you provide it with heat, nickel solid, as a catalyst, and you end up with an alkane. You can also end up with haloalkanes, either by adding a halogen, by adding halogen molecules, or by adding hydrohalogen molecules. The idea is the same. You end up with haloalkane, and you can also end up with alcohol. How? By adding steam to it, right? Now, this is what you used to study in O-level IGCSE, and I'm just going to incorporate it in my mind map before we study the actual mechanism for it. This is not the mechanism. Remember, this is not a mechanism. This is basically the reactions that you were taught in O-level and IGCSE. So a summary that I'm going to write right now, a summary before we look into mechanisms, a summary which I want to write. This is all O-level / IGCSE. A summary from O-level IGCSE is the mind map. So I'm going to start off with crude oil once over again. I'm going to make alkanes. Please, whenever you make mind map, whenever I'm making it, you make it simultaneously with me, please. Alkanes go into alkenes, because alkenes, they only have three reactions: combustion, cracking, and free radical substitution. Through free radical substitution, you make haloalkanes. We don't write combustion in my mind map. I've never written combustion in my mind map, so I won't advise you guys to do that, right? So this is what happens: fractional distillation here. Here, what do you have? Cracking. And you know the conditions for it. I'm not going to write it over and over again. Okay, I'll write it: Al2O3 catalyst, high temperature, and absence of oxygen. Done. And here, what happens in free radical substitution? You just need UV light, which would provide it with activation energy. Done. And haloalkanes, two alkenes. This was a new reaction that you studied in in A levels, which is what? Sodium hydroxide, ethanolic, because we want the OH to act as a base, not as a nucleophile. And you heat under reflux because the reactants are pretty volatile. We don't want them from escaping. And alcohols to alkenes. These are two new reactions which we had studied in A levels, which is aluminum oxide plus heat under reflux. Normally it's just heat, but I would like to use heat under reflux here because alcohols are volatile. Or you could use concentrated acid plus heat under reflux, right? HUR. Now, the reactions from O-level and IGCSE, which I'll incorporate right now, is alkenes going back into alkanes. Alkenes going back into alkanes, alkenes going back into haloalkanes, and alkenes going into alcohols. These are the three reactions which you remember from O-level IGCSE. Number one, how do alkenes go back into alkanes? The only difference is of hydrogen. So I'm going to use hydrogen. So what are the conditions? I'll use nickel solid as conditions and I'll heat it. Done. And alkenes going back into haloalkanes, I can either use halogenation or I could use hydrohalogenation. And the conditions are the same. It happens at RTP in a dark room. Right? Remember this. And then from alkenes to alcohols, you use steam, which is H2O gas. It's called hydration. And you have 300 degrees Celsius temperature. And what? You have concentrated acid as catalyst. And you have a pressure of 60 atmosphere. Conc acid. Normally we used phosphoric acid, acidified phosphoric acid, or acidified sulfuric acid. Now, all three reactions are examples of addition reaction. All three reactions are examples of addition reactions. That's why I'm calling, the reason why I'm calling it addition reaction is because a single product forms, right? And all these white reactions that I've shown right now, the reactions of alkenes, all these white reactions, they are not just called addition reactions, they are called electrophilic addition reaction. It's an electrophilic addition reaction. Now, why is it called an electrophilic addition reaction? Why electrophilic? Why addition? We know why addition, because only a single product forms. Why electrophilic? Why do you call it electrophilic reaction? Why electrophilic? This is what we are going to learn through the mechanism right now. Why is it called electrophilic reaction? The reason why it's called electrophilic reaction has to do with the idea of double bond. It has to do with the idea of double bond, right? It's the electrophile which starts the reaction. It's the electron-loving species which starts the reaction. Now, why is there an why is there an electron-loving species which starts the reaction? Why is there an electron-loving species which starts the reaction? It's because the alkene has a carbon-carbon double bond. The alkene has a carbon-carbon double bond. And the general idea from O-level and IGCSE was that this double bond is going to break. This double bond breaks, right? This is like a double bond. It's going to break. And whenever species you have, this bond is going to break right here. This bond is going to break right here. And A will be bonded to one of the carbon and B will be bonded to the other carbon. Remember this from O-levels IGCSE? Now, the reason why it's called electrophilic addition reaction, addition is because obviously it's a single product. And electrophilic is because you have electrophile which starts this reaction. An electrophile basically starts the reaction. Now, why does the electrophile start the reaction? Why does the electrophile start the reaction? For that, you need to understand what an electrophile is. Electrophile is electron-loving species. Now, where do you find electrons in an alkene? Where do you find electrons in an alkene? Why would there be an electron-loving species making love to an alkene? Why? You don't see electrons, but you see something else. You see, yes, you see area of high electron density. You have a double bond here, which is an area of high electron density. And so if you have an area of high electron density, something which really, really loves electrons is going to come right here. It's going to come right here. It's going to attack this carbon-carbon double bond. And the pi bond, which is the weaker bond, this pi bond, which is the weaker bond, this is the bond which really breaks. It's the pi bond which breaks for alkenes electrophilic reaction to take place, right? So the pi bond breaks and two new sigma bonds forms, right? See, one pi bond breaks and two new sigma bonds form. One pi bond breaks and two new sigma bond forms, right? And the reason why a sigma bond does not break and a pi bond breaks is because we know that sigma bonds are stronger compared to pi bonds. And we know why they are stronger compared to pi bonds. We've already studied this in chapter number 2, that sigma bonds, the reason why they are strong is because it's a head-on overlap. Both the shared pair of electrons lie between the internuclear axis rather than above and below the internuclear axis in pi bonds, right? So sigma bonds are much stronger compared to pi bonds. Hence, when the double bond is breaking, it's the pi bond which really breaks after an electrophile attacks it. After an electrophile attacks it, the pi bond is the fella which breaks and two new sigma bonds form. Right? That's the basic idea of why you call these three reactions as not just addition reaction, rather electrophilic addition reaction. Right? Now, let's go into the detail for it. Basically, I'm going to draw an alkene right in front of your eyes. I'm going to draw a hydrogen here, a hydrogen here, a hydrogen here, and a hydrogen here. This is my alkene. Sorry for my pathetic drawing, but it's an alkene, aka ethene, right? Now, you have ethene right here, and I take a molecule which, let's suppose, is chlorine, or let's say take bromine. Bromine or chlorine, I couldn't care less. Now, this is Br2 which I have written. I'm not going to write it as Br2. I'm going to add it as Br bonded to Br, like this. Now, what happens is, or before I teach Br bonded to Br, I'm going to teach something else. I'm going to call this X and I'm going to call this Y. Right? I'm going to call this X and I'm going to call this Y. Now, let's suppose between X and Y, there is electronegativity difference. And let's say that Y is partial negative and X is partial positive, right? Let's suppose there are permanent dipoles which exist, right? Let's suppose there are permanent dipoles which exist. Now, if there are permanent dipoles which exist in a molecule, aka a partial positive and a partial negative, we also know that there's a partial positive here, partial negative here. The shared pair of electrons would lie closer towards the more electronegative element, which in this case I've called Y. Right? So Y is my more electronegative element. That's why the shared pair of electrons will lie closer towards Y. Okay, great stuff. Now, we also need to appreciate the fact that the carbon-carbon double bond, this area is an area of high electron density. And high electron density areas are attacked by what? They're attacked by electrophile. Species that are electron loving, they are going to attack this area of high electron density. Now, if you look at this molecule actually has this partial positive X. And because this X is partial positive, this is going to act as an electrophile and it will attack the area of high electron density, because we know there is a lot of negativity here. There's a lot of negative charge here, a high concentration of negative charge between the carbon-carbon double bond. And so what really is going to happen is that this partial positive will attack this pi bond, this pi electrons right here, this partial positive will attract this double bond, and the double bond will tend to break. Now the question is, how does it attack it? We know that this species is going to act as an electrophile because it is electron loving, and therefore it will attack this carbon-carbon double bond. That's the reason why we call this reaction as an electrophilic reaction, electrophilic addition reaction. Is because this electrophile is actually what starts the reaction. This is the fella which instigates this pi bond. It's like, hey, I'm partial positive, I'm an electrophile, I'm going to attack you right now because I love electrons, I love areas of high electron density, so I'm going to attack. Now the common mistake that students make is that they say that the attack is going to look something like this. Students, they think that the attack is like this, and this is totally incorrect. Now why is this totally incorrect? Okay, you have to understand that through these curly arrows, through these curved arrows or curly arrows or fish hooks, we actually show the movement of electrons. Yes, it is this fella which attacks this fella, but remember, this fella does not have any electrons, right? This fella does not have any electrons. What happens is the electrons are right here in the carbon-carbon double bond. So you can't show the movement of electrons going from X to this double bond. Rather, what happens is the electrons move from the double bond to this X right here. This is actually what we mean when we say that an electrophile attacks it. It's not actually, the electrophile does actually attack it, but the electrons move from the double bond to this fella right here. Why? Let me tell you in a moment. The reason why electrons move from the double bond to this fella right here is because we show through these curly arrows, we show the movement of electrons, right? Through these curly arrows, we show that two of these electrons, because it's a full-headed fish hook, right? So 2 electrons went to this X. Now the problem is that X has made a single bond here. So what happens is, as soon as these 2 electrons start to go to this X, this bond starts to break heterolytically. The bond starts to break heterolytically because we know X can make one bond, right? X can make a single bond. So if 2 electrons from this double bond go towards X, this fella is going to break heterolytically because already there was an electronegativity difference. So both the electrons would go to Y, and Y would become what? Y would become Y minus, and it would take both the electrons. Y minus would take both the electrons with itself, and what would happen is that you're going to have carbon bonded to carbon, singly bonded to carbon, and you're going to end up with X right here. X is going to bond, and you would have a hydrogen here and a hydrogen here, right? Now the right carbon is, it's up to you. You can put X here or you can put X here. I couldn't care less. You can put X here or here. For this example, I couldn't care less, right? Now there's Y minus which is left. Y minus is left. And the carbon, this carbon right here, it has made 3 bonds and it has lost 2 of its electrons, which means it is going to make a carbocation intermediate. There must be a positive charge, a complete positive charge on this particular carbon. Why? Because 2 of these electrons went from this pi bond and went to X, and this X got bonded right here to the left carbon. So this carbon is now deprived of 2 electrons, hence there's a positive charge right here, because 1 electron belonged to this carbon and 1 electron belonged to this carbon, and since both went, this carbon is now deprived of its electron, hence a positive charge right here. And because now there's a positive charge and there's a negative charge, this Y minus is the fella which attacks this positive carbon right now. And see the movement of electrons. 2 of these electrons are going to go make a dative bond right here with this particular carbon. And so what really happens is the Y bonds to it. Right? So you have C double bonded to C, singly bonded to hydrogens, bonded to X, bonded to C, bonded to 2 hydrogens. And so this is the Y which bonds. Now you might say, sir, but there are a lot of common confusion and common questions of students. We call this fella as carbocation intermediate. We've already studied what carbocations are. Carbocation intermediate. It's an intermediate stage which forms. Right? It only occurs for a split second, and then the Y minus actually stabilizes this positive charge and bonds to it. Some common questions from students. Sir, why are you calling it an electrophilic reaction? Electrophilic addition reaction. Addition because a single product forms. Electrophilic addition reaction. Electrophilic because the reaction is started off by electrophile. And remember, the electrons move from the double bond to this electrophile right here, not the other way around. Because this electrophile is already deprived of electrons since the bond breaks heterolytically. Both the electrons go here. This does not have any electrons once the bond breaks. So electrons must travel from the double bond to this X right here, not the other way around. This is one common confusion. Second confusion that students have is, sir, isn't Y minus a nucleophile? Yes. Any questions, guys? Isn't Y minus a nucleophile? Shouldn't this question come in your brain? Absolutely. It is a nucleophile because it has a lone pair and it's being bonded to. So then why don't you call it a nucleophilic addition reaction? This is a common question because the reaction is not started with a nucleophile. Once in the exam it was tested that in alkenes addition reaction, an electrophile attacks in stage 1 and in stage 2, in the second step, a nucleophile attacks. And every student got that MCQ wrong because they never knew that a nucleophile also attacks. It's a nucleophile, appreciate it. It has a lone pair, it's negatively charged, it's going to attack it right here. Both the electrons from the nucleophile will come here and make this dative bond. Absolutely, it will happen. Absolutely. But the reason why it's called electrophilic reaction is because an electrophile starts it. Yes, there's a nucleophile involved in step 2 right here, but we couldn't care less. This is a nucleophile. I want you to appreciate it. Done? Now let's move on to the idea, the proper idea for it. The proper idea. Let's start learning the mechanism. Number 1, I'm going to start off with this mechanism right here, which is electrophilic addition of halogen or halogenation. So now let's start learning the mechanisms. Halogenation or electrophilic addition, EA, electrophilic addition of halogens. Let's learn this mechanism. In this, again, the conditions are at RTP and in a dark room. But what actually is the mechanism? What actually is the mechanism? I'm going to first use bromine as an example. And this is also called bromination, by the way. You can also call it bromination, halogenation, aka bromination, chlorination, and so on and so forth. Now, one thing that you need to keep in mind is that when bromination takes place, for example, you have an alkene C2H4 and bromine gets added to it, you're going to end up with what? C2H4Br2. Right? This is called bromination. And the conditions are, it'll happen at RTP, at room temperature and pressure in a dark room. This is the condition for it, right? And the reagent is bromine. Now, if you're using bromine aqueous, you know that bromine aqueous's color is what? It's orange. Bromine aqueous is orange, by the way. And bromine liquid is brown. You need to know this, right? Bromine liquid is brown and bromine aqueous is orange. Now, if you're using bromine liquid, the idea is that the color of bromine, which is brown right here, it will go colorless because both the bromine atoms will get added to the alkene, and you're no longer gonna have Br2. You're gonna have C2H4Br2, which is a haloalkane, and this is colorless. So as soon as the Br2 gets bonded to these alkenes, you're going to end up with C2H4Br2, which is colorless. So you can either go from brown to colorless, if you're using Br2 liquid, that's going to be the observation, or either you're going to go from orange to colorless. That's going to be the observation because Br2 aqueous is orange. Done. Now let's look into bromination. I'm going to use Br2 liquid, by the way. I'll tell you why I'm using Br2 liquid in the upcoming classes. For now, I just am concerned about using Br2 liquid. See, I'm going to take my alkene, which is carbon-carbon double bond. This is hydrogen, and pay very, very close attention here. Tawajjo. Right. Now what's going to happen? There is a Br2 molecule right here. Are there any permanent dipoles in a Br2 molecule? Are there any permanent dipoles in a Br2 molecule? No, it's a non-polar molecule. There are no permanent dipoles, are there? There are no permanent dipoles, are there? No. In my example, the one that I taught you guys above, there were permanent dipoles which existed. What about this? There are no permanent dipoles. How is the Br going to be added to the carbons? Because understand that we know that it's an electrophilic reaction, it's an electrophilic addition reaction, an electrophile must start the reaction. And two of these electrons will go to the electrophile. Now the question is, there are no permanent dipoles here, are they? How will this act as an electrophile? No permanent dipoles. Basically, You now have to start visualizing. Understand the story. Basically, what happens is Br2 and ethene, they start to approach each other. They're like, hey, hey, what's up? What's going? They're in this mixture and they start to approach each other. Now, what happens is when they're approaching each other, this Br2 sometimes gets so close to this carbon-carbon double bond. This Br2 can get so close to the carbon-carbon double bond right here, the one that I'm showing right now. Let me try and, if I can just show it. Okay, I can. But understand that this this Br gets so close to the double bond, and we know that the double bond is an area of high electron density. So what this double bond does is this, because there's high electron density, this double bond ends up pushing these two electrons. These two electrons are shared dead center, aren't they? These two electrons are shared dead center between these two because there's no electronegativity difference between Br and Br. But sometimes they get so close to the carbon-carbon double bond that this double bond electrons pushes these two electrons further away from themselves. And when they push it further away, what happens is that the two electrons, for a split second in time, they come very close to this Br right here. The Br which is bonded away from this double bond, right? So what this double bond does is when these atoms get too close to the carbon-carbon double bond, it repels the pair of electrons. It repels the pair of electrons in the Br-Br bond, and they repel it away from the nearer Br atom. They repel it away from the nearer Br atom. So this Br atom is closer towards this carbon-carbon double bond. They push the electrons in this double bond, right, in this single bond right here, and they're closer towards the Br atom, which is further away from the double bond, right? And so what really happens is that through this pushing of electrons, this Br becomes partial positive and this becomes partial negative, doesn't it? Because now the shared pair of electrons lay closer towards the Br atom, which is further away from the carbon-carbon double bond. And this makes the Br atom, which is closer to the carbon-carbon double bond, slightly positive, and the further Br atom becomes slightly negative. And the slight Br positive now can act, this slightly positive Br atom, it can attract the pi electrons. It can attract these pi electrons towards itself. And therefore, it can form the CBr bond. So what happens is now this can act as an electrophile. The pi electrons will go right here towards this Br, but we know Br can only make one bond. What about the already existing bond? So the already existent bond will break. Both the electrons will go to the Br atom, which is on the farther end. And the CBr bond will form. Now you can form the CBr bond on the left carbon and on the right carbon. It doesn't really matter because it's a symmetrical alkene. I couldn't care less. I'm going to make the Br right here. Make sure that the Br bond's right here. And this carbon becomes a carbocation. This carbon is a carbocation. Right? And it's what carbocation? It's a secondary carbocation, right? Secondary carbocation. Why is it a secondary carbocation? Because the carbon is bonded to an alkyl group. So it's a secondary carbocation which forms. Done. Now, secondary carbocation is in the mixture, and this is also called intermediate, carbocation intermediate, because this exists for a very split second. Why? Because what happens is now in the mixture you also have the Br minus. You also have the bromide ion, don't you? Because both these electrons were taken in by this Br. I'm going to represent it with a dot and cross maybe. It doesn't matter how you represent it with two dots or with a dot and cross. I represented it with a dot and cross in this bond right here, so I'll write dot and cross here. And so if there's two electrons right here and a negative charge and there's a positive carbocation, what will happen? This fella will now act as a nucleophile and both these electrons would go here. Wouldn't it? Let me make the arrow slightly better. Both the electrons would go right here. See? And the second Br will also then bond to it. And so this is the reason why it's known as electrophilic addition. Done. So the story is pretty simple. If I were to recap my story, and this is the mechanism for it. How easy is the mechanism? You need to understand the story. क्या होता है? The Br2 and the C double bonded to C approach each other. Right? The Br2 and the carbon-carbon double bond approach each other. The area of high electron density around the carbon-carbon double bond repels the pair of electrons in the Br-Br bond away from the nearer Br atom. And what happens is this makes the Br atom, which is closer to the C double bonded to C, slightly positive, and the further Br atom slightly negative. And the slightly positive Br atom then attracts the pi electrons and forms a covalent bond with carbon. It forms the CBr covalent bond. At the same time, the Br-Br sigma bond breaks heterolytically. It breaks heterolytically, and both electrons in the broken bond go to the same atom, which is this Br atom, which is further away. And then it ends up with a bromide ion. The bromide ion attacks the carbocation intermediate, and the final product forms right here. That's the story for it. That's the story. And please, you have to show the arrows just like I'm showing right here. These are the arrows for it. Let me even show you guys a picture. Let me see if I have a picture. Sorry. Let me see if I have a picture. If I do, me shows you the picture. Okay. So me shows pictures. I'm gonna show you. Asan or mushkil? There's nothing difficult about this. I swear. There's nothing difficult about this. Ore sajna. Let me see. I think this is the... Nope. Oh, give me a moment, guys. Let me check out the picture. Finally found the picture. See? This is what happens. This is the mechanism for it. So, what happens is carbon-carbon double bond. These two approach each other. The double bond electrons, since it's an area of high electron density, it ends up pushing the shared pair of electrons closer towards the Br atom, which is on the farther end. This makes this Br atom slightly positive, this slightly negative. The pi bond, the electrons from the pi bond attack this partial positive electrophile. Once they attack it, a CBr bond forms, but simultaneously this Br-Br bond must break, because Br can only make a single bond. So this, in order for the CBr bond to form, this bond must break heterolytically, not homo, heterolytically. And therefore, once it breaks heterolytically, what's going to happen is both the electrons in the shared pair goes towards this Br. This Br this Br ion, the bromide ion, then attacks this carbocation, forms the second bond right here. Done. That's it. Now I have a question. What if you have an asymmetrical alkene? We already have studied it, by the way. Asymmetrical alkene. Asymmetrical alkene means, for example, you have carbon bonded to single. There's no symmetry, right? Bonded to this carbon. You have 3 hydrogens here, 1 here, and 2 hydrogens here. My question to you guys is, which two products can form? Which two products to nahi khair? If it reacts with the Br bonded to Br, where would the Br go? Would the Br go on the A carbon, or would the Br go on the B carbon? Right here. That's the question. That's the question. Would it go on A carbon, or would it go on B carbon? What's going to happen? A carbon or B carbon? Hey. A or B? That's the question. Let's talk about it. Basically, the double bond, area of high electron density, is going to push the electrons in the Br-Br bond away from each other, away from the Br which is closer to this, and closer towards the Br which is farther away from this double bond. And so this will make this slightly positive, slightly negative, and then the pi electrons are going to attack this Br fella right here, which is the electrophile. Both the electrons in the shared pair electrons will go towards the other Br which is farther away, and the bond will break heterolytically. The question is, would you end up with this electrophile? Sorry, would you end up with this carbocation, CH3, bonded to a carbon which is bonded to hydrogen, and the Br coming here and this forming, this becoming the carbocation? or do you end up with the Br going on this carbon atom? Do you end up with the Br going on the carbon atom which is on the right here, and this carbocation forming? You use your brain and tell me which is more likely between these two. Which is more likely? Obviously you have the Br minus here, the Br minus, both the electrons from the Br minus would go here, and you could say both the electrons from the Br minus would go here. Then my question to you is, which is more likely, number A, I'll call this number A or number B? Use your brain. It has to do with the stability of carbocation, which we've already studied. This is a primary carbocation, and whereas this is a secondary carbocation. We know a secondary carbocation is more stable compared to a primary carbocation because of the alkyl positive inductive effect. We all know that, and we've studied it in a lot of detail, that the alkyl groups, they are electron donating, and therefore it will stabilize this positive charge, and therefore this becomes more stable. But between 1 and 2, which one is more likely to form? There can be two products forming, but the major part is this fella right here. This is more likely because this fella is energetically more favorable. Right? There is a stable carbocation which forms, and we want a stable carbocation to form. For example, if I show it graphically to you guys, let's suppose, oh my god, pathetic, Suleiman, pathetic. Oh my god, my drawing is very ganda, very kharab. Sorry for that, guys, but just for the sake of example, which one is A and which one is B? Which one is A in this? If this is the energy profile diagram for it, which one is A and which one is B? These MCQs have never been tested. It can be tested in the future, who knows. This is step 1 where the attack happens. This is step 2 where the attack of the nucleophile happens. This is the carbocation intermediate. This is the carbocation. This is intermediate. This is also intermediate. Which one is A and which one is B? We know that B is a more stable carbocation right here. This B is more stable carbocation. And let me also change this, right? Let me also call this चलो सही है. अच्छा, A B में confuse नहीं होना चाह रहा बच्चों को. खैर, तो which one is more likely to form? The orange line or the blue line? Obviously, the blue line is more likely to form because see, this carbocation intermediate is at a lower energy level. This carbocation intermediate is at a lower energy level, which means it is more stable. The lower the energy, the greater the stability. So probably this energy line is for this guy, and this energy line is for this guy. Absolutely, you're right, Salahuddin. Great job. Done. So you need to keep this in mind. The more stable intermediate, which fella is more stable? This is a secondary carbocation, so this is more likely to form compared to the above one. Done. So we're done with the first reaction for alkenes, the first reaction mechanism. We're done with almost all the reactions, but the first reaction mechanism of alkene is done, and this needs to be known to you guys. I'm writing first here because this is the reaction mechanism for it. I want you guys to make the curly arrows on your own. Please do it. Please do it on your own. Let's suppose I give you guys an alkene, which is right here. Tuck, tuck, tuck. This is now a symmetrical alkene, so it doesn't really matter. But I want you guys to react it with Cl bonded to Cl. Shabash. I want all the curly arrows. Tuck. And this is a question mark here. This box is a question mark, and then the final product. Shabash. This is step 1. This is intermediate forming, and then this is step 2. Shabash. Do it on your own. Do it. So I know you guys know the story behind it. Shabash. Do it. Vanya, were you messaging me the other day? कि सर वो सर ने ये पढ़ाया, कुछ समझ नहीं आया. I hope you've understood it now, Manya. अब समझ आ रही है? Manya, you're understanding the mechanism now? It's just all about arrows, all the arrows. And this is how you go from an alkene into a haloalkene. Done, sir. वानिया समझ आ रही है? तू थोड़ी देर और ठहर जा. How I do this on your own, guys? Now I'm gonna do it since you guys, some of you answered, some of you didn't. What's going to happen? The area of high electron density pushes the electrons in this double bond away towards this Cl, which is further away from the double bond, and this Cl therefore becomes slightly positive. This Cl becomes slightly negative, and now two of these electrons from the pi bond. The pi bond is the one which breaks, not the sigma one, because pi is weaker than sigma. Two electrons go here, but I know Cl can only make one bond, and so if it can only make one bond, this bond must break, and it breaks heterolytically because two electrons have already been pushed away by this double bond towards the Cl, which is farther away from the double bond, and so this breaks heterolytically. Heterolytic fission takes place, and you end up with a carbocation intermediate. So tuck 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 tuck, the Cl bonded here, and this fella became the carbocation intermediate. It's a primary carbocation, but it's a primary carbocation, but the Cl did not bond here, it bonded here. Not primary, a secondary carbocation, but it happens right here. This is the Cl which bonded, and this fella became the carbocation intermediate. It's a symmetrical alkene, so it doesn't matter. You can make this carbocation intermediate, this carbocation intermediate, doesn't really matter. And the other Cl right here, the one which now has both the electrons, this will now attack this fella, and you're going to end up with an alkene. Tuck 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 tuck. So it happens in two steps, tuck and tuck. That's all. That's literally it. I've even shown you guys the energetics for it. That's it. Can you guys do this for me, please? Last example. Cl bonded to Cl. Somebody. What are the conditions for it? This will happen in a dark room at RTP. There are no conditions. Hence we say at RTP, in a dark room, this will also take place. Done, sir? Okay. So what's going to happen? What's going to happen? Sir, the pi, this will become partial positive, this will become partial negative. Why? We already know the story. The pi electrons, this high electron density pushes away the electrons in the Cl-Cl bond further away towards the Cl atom, which is further away from the double bond, and therefore this becomes slightly negative, slightly positive. The shared pair of electrons lie closer towards the Cl, and this pi electrons attack the Cl right now. It's going to attack the Cl. This bond is going to break heterolytically because two of the electrons which lay closer towards the Cl atom need to break this bond in order for this CCl bond to form, right? And so what ends up happening is you have Ca, Cl, Cl, tuck, 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 tuck. Now you tell me, should I bond the Cl right here or should I bond the Cl right here? To the left carbon or to the right carbon? Which is more likely? A is more likely or B is more likely? Where would the Cl go? See, you need to make a carbocation which is more stable, and we know that this is primary. If the Cl goes here, then this fella is the carbocation, and this fella is less stable. It's primary carbocation, right? Or secondary carbocation, right? Because it's bonded to an alkyl group right here. But if it goes here, why am I saying secondary? Sorry, primary. Why am I saying secondary? My bad. This fella is bonded to one alkyl group, hence this is primary carbocation if this fella were to form. But if the Cl goes here and this fella becomes the carbocation, this fella has the positive charge, then this is the secondary carbocation because now it's bonded to two alkyl groups, right? So between A and B, where should the Cl go? We know that secondary carbocation is more stable than the primary carbocation, and therefore the Cl that should bond here, the Cl that should come, should bond with this carbon in order for this fella to be the carbocation. We know that two products can form. We know that this can also happen where the Cl actually goes here and this becomes carbocation. Absolutely, this can also happen, but this is less likely. This is more likely. So sometimes if the examiner gives you two options, you show both the options. If he doesn't, then you go for the one which is more likely. And so you also have a Cl minus inside this mixture, and the chloride ion is now going to attack this fella and it'll form the product. Tuck, 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 Cl, tuck, 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 and this is the Cl that bonded. Yeah, this is more likely. And you could have also thought about this कि चलो वो मैं नहीं बताना चाहता. Markovnikov's rules इधर नहीं लगाते. You think from the perspective of stability of the carbocation. Yes, this can also form, but it is less likely. This can also form, but again less likely. Cl. you know, ठक ठुक Cl को ऐसे लिख लेते हैं, सही. Done, guys. Any questions in the electrophilic addition reaction? Any questions, guys? Done? No questions? Easy peasy lemon squeezy. So we're done with the first bit. From our mind map, we're just done with this particular mechanism. This is what you need to know. This mechanism right here, electro elimination, this elimination mechanism right here, this fella, alcohol to alkenes and haloalkanes to alkenes, these mechanisms aren't part of your course. This mechanism is part of your course, and so is this mechanism. So these two mechanisms are part of your course. Other than this, no other mechanism for alkenes is part of your course. I think मैं तो hydrohalogenation भी पढ़ा दूँ, उसमें कुछ भी नहीं है. Hydrohalogenation is the same idea. It's the same idea, guys. Do you want me to show it to you? बिल्कुल simple, बिल्कुल simple. It's the same idea. I'd like to show it to you. I'd like to show it to you. Hydrohalogenation, I'd like to show it to you. It's the same idea. Right? So I also want to finish this HCl bit. The same idea works in hydrohalogenation. Okay? See, the first example that I gave was of hydrohalogenation. Right? How does it happen? So let's suppose you have an alkene, tuck, tuck, tuck. We're going to make a symmetrical alkene, tuck, 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 tuck. Right. Now, it's H and it's Cl. The same idea happens. There's already permanent dipoles which exist here. You don't have the story of Cl. You don't have the story of Br. There, here in hydrohalogen, a permanent dipole already exists, because we know that Cl is more electronegative than hydrogen. Therefore, automatically the shared pair of electrons lie closer to the Cl atom. And if they lie closer towards the Cl atom, we know that this double bond is going to attract this hydrogen right here, and we know hydrogen can only make one bond, so the shared pair of electrons, since they are not shared evenly between the two, heterolytic fission will take place. Both the electrons will go towards the Cl, and it's going to form C, single bonded to C, 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 and it's going to form a bond with a hydrogen, and this fella is the carbocation, which is now going to be attacked by the Cl, tuck, 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 and this is the reaction mechanism for it. That's it. That's all. But what if it's an asymmetrical alkene? Then you have to use your brain. Then you have to think about the stability of carbocation. Right? Think about it on your own. Use your brain, sir. Use your brain. If here you have H bonded to Cl, this is partial positive, that's partial negative, or let me make the partial positive here. Partial positive, partial negative. The shared pair of electrons are already lying closer towards the Cl. Both the electrons go here. Once this fella attacks this fella, you know, the electrophile attacks the pi electrons, or the pi electrons are pulled by the electrophile. C, single bonded to C, single bonded to C. The double bond breaks, obviously. Tuck, tuck. Now the question is, where does the H bond? That's the question. Where does the H bond? Does the H bond here, or does the H bond here? Now here you can use two ideas. It's up to you, whichever one you want to use. I want to use the idea of stability. Since as a teacher, I will always recommend to use concept and not rules. But you'll find a lot of teachers teaching you rules. I'll also teach you rules, and I have taught you rules. Markovnikov's rule, the more substituted carbon rule. I've taught you guys a lot of rules in Intro to Organic Chemistry. But here, I would want you guys to use your brain. Tell me something. Which is more stable? Which is more likely? A positive charge here is more likely, or a positive charge here is more likely? Is a secondary carbocation more likely, or a primary? We know secondary is more stable compared to primary. Therefore, secondary is more likely. So this carbocation would form here, and here you would have the H bonding, right? Obviously, this can also form. I'm not saying it can't. It can, but it's less likely. The hydrogen bonding here, this becoming the carbocation, and the hydrogen bonding here. This can also happen, but it's less likely. We all know that. Now, you could either use the idea of stability, or more likely, or you could use the idea of Markovnikov's rule, where Markovnikov said that, hey, the hydrogen would bond, the hydrogen right here, the hydrogen would bond to the carbon which has more hydrogens. So which of these carbons between these two, this carbon has one hydrogen, this had two, so the hydrogen would bond to the carbon which has more hydrogens. You just bond the hydrogen here. It's up to you. Either you use rule or you use logic. I prefer using logic. I prefer using concepts rather than rules. But you could have used Markovnikov's rule, which is that the hydrogen would bond to the carbon which has more hydrogens. Here this carbon has two, this has one, it would bond here. But if the examiner asks you, why does the secondary carbocation form compared to primary, don't say the hydrogen would bond there. Then you explain it to the examiner that the secondary carbocation is more stable than the primary carbocation, therefore it's more likely. Why is it more stable? Because of the positive alkyl inductive effect, wherein the alkyl groups are electron donating, which stabilizes the positive charge on the secondary carbocation compared to the primary carbocation, right? And hence the charge spreads out on the secondary carbocation and it is stabilized. Hence secondary carbocation, since it's more stable, it's more likely to form, right? And then you also have the chloride ion. So I'm going to show the chloride ion right here, and it's going to go like this, tuck tuck. This chloride ion, you're going to go like this, and you're going to end up with products. So this fella is more likely, this fella 2-bromo propane is more likely compared to 1-bromo 1-chloropropane, or 2-chloropropane is more likely compared to 1-chloropropane. Understand, this is 2-chloro and this is 1-chloro. Which one is more likely? If the examiner were to ask you which one is more likely, 2 or 1, obviously 2-chloropropane is more likely, because the carbocation intermediate, the secondary carbocation intermediate, is more stable than the primary carbocation intermediate. Please, there's one common misconception. Students, they tend to use these things and twist them in such a manner that they ruin their entire concepts. Do not state, please, I beg you, do not state that a secondary haloalkane is more stable than a primary haloalkane. No, don't state this, because they're equally stable. This is where the MCQs are going to kill you. MCQs will say secondary this secondary haloalkane forms compared to a primary haloalkane because secondary haloalkane is more stable. Zero. No, secondary haloalkane is not more stable than primary haloalkane. They are equally stable. It is the secondary carbocation which is more stable than the primary carbocation. It is the intermediate which is more stable than the primary intermediate. Please, these two are equally stable. If you did not know this, now you know it. These are equally stable. It is this which is more stable than this. Please, please, please. So did you guys know that primary and secondary haloalkanes, they are both equally stable? It's the secondary carbocation which is more stable than the primary carbocation. Hence 2-chloropropane is more likely to form compared to 1-chloropropane. Done? So we're done with 2 of the reaction mechanisms. Pretty basic, pretty simple. We'll do a lot of examples, and this is, frankly speaking, this is it. We're done with this. 1 and 2. And these 2 are part of your course. You need to know them. Only these 2 are part of your course, nothing else. You don't have this as part of your course, and you don't have this as part of your course. I'll just show you a picture for this, and I'll do this for you, but I'll just show a picture for this because it has to do with a catalyst, desorption, and so on and so forth. This mechanism isn't part of your course, and neither is this, nor is this, nor is this. You just had these 2. That's all. For alkenes, these are the 2 mechanisms part of your course. We are going to jump into more and more examples in tomorrow's class, but I will also explain this mechanism to you, and I'll show you a picture for this mechanism because I couldn't care less. Any questions up until now? We're done with both the mechanisms for alkenes. We're done with both the mechanisms for alkenes, and I can even show you a picture for it. If you want, I can show you a picture for it. If you want, that is. Because pictures are much better than my drawing. Hence me shows. Pictures are better than my drawings. Pictures are better than my drawings. Pictures are better than my drawings. Manhoos, where are the pictures? If you want to see this picture, I also have this picture. Here you go. This is the mechanism. This is the reaction mechanism for hydrogen. Alkenes an alkene reacting with hydrogen, this is the reaction mechanism for it, not part of your course. You just need to know when alkenes react with halogen, nickel solid or platinum. You can even use platinum. Nickel solid / platinum is the catalyst, and you heat it. Right? It's about 100 to 200 degrees Celsius, but you heat it, right? And you end up with alkanes. This is the mechanism. Those who are interested in chemistry can look at this mechanism and try to figure it out on their own. I'm not going to go into the detail for this mechanism since it's not part of your course. Basically what happens is this hydrogen gets bonded to this, then desorption takes place, and so on and so forth. But this mechanism will never be tested since it's not part of either Pearson, neither Cambridge nor IB. It's not part of any of your course. Okay. This is the mechanism. Done. Then I can even show you the mechanism, or not the mechanism. I can show you this mechanism. Sorry, BR. What the hell? I think this is it. Done. Where's the picture? My god. Do I not have picture? You guys can check this picture out. See, this is what happened. There are already charges that exist. There are already permanent dipoles which exist. Tuck, electrophile, hence called electrophilic addition. Tuck. That's what happens. But this is symmetric alkene. Asymmetrical alkenes, books won't discuss it. I have discussed it since exams discuss it as well. Done. And if you want to see the reaction mechanism for this fella, I can even show it to you guys for this hydration reaction where alkenes go into alcohols. I can show you the mechanism for it if you want. That is. You want to see the mechanism for it? It's pretty basic. It's basically the same as the elimination, the one that I showed you guys in elimination. The idea is largely the same. You want me to show it to you? Sir, please do. Okay. See, it's like this. Basically, when you take an alkene, let's suppose I took this particular alkene. This is H. This is about, like, let's suppose this is CH3. Let's suppose this is hydrogen. Let's suppose this is hydrogen. It'll make you guys remember it as well. Again, what are we using? We are using concentrated acid plus we are using, that's our catalyst, right? We are using 60 atm pressure and we are using 300 degrees Celsius, right? This is what we are using. And you go from alkenes into alcohols, right? You go from alkenes into alcohols, right? Sorry, why am I saying acid? It's H2O. H2O gas, and acid is my catalyst, right? My reagent is H2O and acid, concentrated acid, is my catalyst. Now what happens is, normally if you were to write this reaction H2O gas, you can put the hydrogen on any of the carbons, obviously, and on one of the carbons you get the OH, on one of the carbons you get the H, and that's how you went from an alkene into an alcohol, right? That's how the double bond breaks. The H either goes here or here. It's a symmetric alkene, and the OH goes on the other bit, right? Now what really happens is the mechanism looks something like this. This is how the mechanism looks like, but again, not part of your course. You'll never be tested on this mechanism. Hota ye hai that since the acid is the catalyst, you have a hydrogen ion. Because of the acid, you have a hydrogen ion, and because you have a hydrogen ion, the area of high electron density is gonna attack this hydrogen ion, and hence it's an electrophilic addition reaction. Why electrophilic addition? Because an electrophile starts this reaction. So what happens is it attacks this fella right here, and what you end up with is the double bond breaks. You end up with, let's suppose I'm gonna reverse this, right? So I'm gonna put a CH3C bonded to C, singly bonded to this C. This is my CH3. This is my hydrogen, and this is my CH3 now, and this becomes a positive cation. This becomes the cation, right? This becomes the carbocation. This hydrogen bonds here with this carbon, so CH1, H2, H3. That's why I've just written CH3 like so. Okay. This becomes the positive carbocation, and what then happens is, since you also have H2O, the H2O fella, the O bonded to two hydrogens right here, this will now attack the carbocation. So since it has a lone pair, H2O has a lone pair, this lone pair will attack the carbocation intermediate. But we know that H2O can't make 3 bonds, it has to make 2 bonds. So the moment this fella attacks this fella, we know that the moment this fella attacks this fella, the hydrogen, one of the OH bonds, it will tend to break. One of the OH bond will tend to break because oxygen again is pretty electronegative. It will want its electrons back. It would want its electrons back, right? So the moment these two electrons go here, this OH bond breaks and both the electrons go right here. So you end up with C being bonded to H, being bonded to CH3, being bonded to OH, and then being bonded to a CH3, and you end up with a hydrogen ion, right? You end up with a hydrogen ion, and this is how the alcohol actually forms. And that's why I said that the acid is the catalyst, because it started the reaction, and after the OH bonded, the H2O bonded to it, the OH bond broke, and you ended up with a hydrogen ion all over again. Muhammad Salahuddin, I said this at the start, this will not come in your exam. I said this 50 times, I believe, at the start of this class. The only two mechanisms as part of your alkenes course is the chlorine addition or the bromine addition or the HCl or HBr addition. Okay? So this is not part of your course, but it's pretty basic, right? The catalyst starts the reaction. This is an electrophile. Tuck, add it. Carbocation forms. H2O, because you're using steam, right? So this steam, the H2O fella, this is gonna, the lone pair of the H2O attacks here, but because oxygen is pretty electronegative, it'll want the lone pair back to itself, so it breaks the OH bond to get the lone pair right here, and a hydrogen ion exists. And I can show you guys the picture for it. See it and absorb it and enjoy it. I think it's 7:10 if I'm not wrong. Here you go. देखिएगा, the double bond attack this fella, a CH bond formed. This is CH3, CH. This became the carbocation intermediate. Why this? Why not this? 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 Because as per Markov-Kovnikov's rule, the hydrogen bond should bond to the carbon with more hydrogens, or this is a more stable carbocation, so this is more likely to form, right? More likely to form. So this carbocation forms right here. The H2O का जो lone pair है, it bonds right here, and because O is very electronegative, it will take the electrons back in, and a hydrogen ion forms. This bond breaks, hydrogen ion forms, and the OH is happy. Everything is happy. Done. So this is the reaction mechanism for it. Nobody cares. Nobody couldn't care less. I couldn't care less. You shouldn't care less. But the idea is that these two mechanisms need to be known to you guys. These two are part of your course. This isn't, hence I just showed a picture. This isn't, but I showed it, and I even showed the picture. This isn't, none of this is, but I've shown you guys this as well. I've shown you guys somewhat of this. I've shown a picture for this, but these two are the only two which will be tested in your exams. I'm saying this over and over again. Please do not message me a billion times. Only these two are part of your course. Done? Any questions, guys? आसान है, मुश्किल है?